don't stand here. I was literally like this. Did you see me? Reach across me. I was like waiting for that. But I wasn't. I was contained. You were contained. You made it harder.
So, good morning. So, you should answer this question based on your abilities. And survey says we've got a distribution. Well, this device has a name. Newton's ring, or Newton's wheel, rather, because he used it to demonstrate the fact that white color doesn't exist. It's a combination of all so when we see white, it means we see all of them simultaneously. This also demonstrates that our vision has some inertia. It processes light in portions. That's what people use to make movies. Yeah. Many frames, one after another, looked as a continuous process for us. So it's white because all possible colors being reflected by this space. It would have been black if no light would be reflected at all. And it's blue because blue is reflected, and it's red because red is reflected. So this is a review, and let's try to look at it one more time from a different perspective. Maybe that would look better. Let's try this. So what do we have? See them open. So this is a mirror, flat mirror. All we need is a source. Single ray. Better. So You just worked. All right. Lazy bulb. So a single beam, single light ray is reflected according to law of reflection. Work. I need you. That's weird. This is physics. Always have a backup. And the backup for the backup. Okay. So, well, I will remember this. I remember everything. So that's a mirror. And you see, if we have several rays parallel to each other, they remain parallel, specular reflection. And if we replace this mirror with concave mirror, we can see now this guy. Go there. We can see that all rays parallel to each other after reflection go through the same point. That's what we call focal point. This is what we call focal distance. And people who designed the system never taught any class. So what we have now, again, is a mirror, but now it's a convex mirror, and we can see rays traveling toward, reflected, away from the middle line, which also has a name, a principal axis. So what do? That's what we do every time when that happens. We use extensions, and the extensions now cross. So this situation has a name, conversion. That's why we call this type of a mirror a conversion device, and this situation we call diversion. So that's what we call a diversion device. Now, we know that for a mirror of any type, we can write two equations. But you can see only one letter. Where is it? Oh, here, that's the equation. And a second equation for the magnification, which has two parts. The first part is a definition of what it is, and second part comes from geometry. Oh, now it's red. Where is it? Here. See? Now, so far, we don't know much about lenses, but we know that they work because of the phenomenon we call refraction. Refraction, bending light, straight. Now what's going to happen? Oh, come on. It's bent. This is a water prism, just a triangular plastic vessel filled up with water. Well, if we use a lens which is thick in the middle and thinner on the edges, what's happening? Well, we can see that the rays converge. Can you? Eventually. So that's why we have a marker. Rays which are parallel to each other after traveling through a lens go through the same point. That's the focal distance now. And the difference between a mirror and a lens. For the lens and for the mirror, the focal point is on the different sides. For the lens, it's behind the lens, and for a mirror, for conversion device, it's on the same side. This is a conversion device, conversion lens, and this is a diversion device, diversion lens. Rays diverge, and again, every time when it happens, when rays actually travel bending away from the middle line, what we use is extensions, because extensions will converge. This will be the focal point, focal distance, but for a diversion device, it has to be negative. So not for sale. Now, these equations should make even more sense. They're all related to a specific device. All devices, except simple flat mirror, either converge light or diverge light. When it's a conversion device, the focal point is real, focal distance is positive, and it can form actual real images, but a diverging device cannot form a real image. It only can form a virtual, imaginary image. And the standard strategy for any problem always starts from a diagram, and the diagram has elements, so we have to draw all elements, principal axis, the device, important points, starting from a focal point, an object, then actual rays, and you can use only 2 rays. 2 rays are sufficient. You can do more, but 2 is sufficient, and then you can see an image, write 2 equations, and solve those equations. Well, so please do that. Probably I'm going to take it. Well, so you should draw the picture, and I should draw the picture as well. These are the steps, just in case. So, principal axis is that middle line goes through the middle point of a device, perpendicularly to the device. Now, where is it? We don't know. We pick any point, it doesn't matter. Normally somewhere in the middle, because we don't know where we should place an object, where will be the image. Now, this is just a location of this device. This is the whole device. But now we have to show what kind of a device is that. And Suddenly, I get thirsty for coffee, and for better digestion, I'm going to drink it while walking. You know that drinks are restricted. Yes. Oh, yes. Sorry. And my lens is concave. So that would have been maybe even a right problem, but different from this one. And we don't want to solve a different problem. We want to solve the problem we have to solve. It's like an exam. You can solve any problems, but if they're different, not going to be graded, right? So, but we can, oh no, that's not the way I do it, right? I forgot. This is the right way to do it. So let's start again. If you didn't succeed first time, start and try again, but try something different, because doing the same thing, expecting different results, is not wise. So this is a convex mirror. And for the convex mirror, first of all, what we know is any ray traveling parallel to principal axis after reflection should bounce back, but the right way to draw that ray is using a focal point. So out of several possible options, only one is correct. Well, this mirror could have been a cut of a sphere, or it could have been just a large sphere, shiny, large sphere. Doesn't really matter. Yeah. We don't really care about this part. So we have to indicate the location of a focal point, and this focal point should be at what distance from the middle point of the mirror? So the radius of the curvature is 60. The magnitude of the focal distance equals 1/2 of the radius, which is actually 1/4 of a diameter, if by any chance we have a diameter known. So the actual value, because it's a diversion device, should be negative, which tells us negative 30 centimeters, right? Radius 60. Now, we don't draw a ray yet. In this situation, again, first we draw a would have been extension of that ray. And then we continue with the actual ray. Yes? Because it's virtual, not real. It's only in our mind. There is no light behind the mirror. We have to imagine that this point exists. No, what specifically? Because there is no light behind the mirror.
So because it's convex?
Because it's convex, because that's a good thing to compare. For a concave mirror, rays would converge on the same side. Actual focal point would have been, well, on the left relative to us. And if we follow standard agreement, place an object to the left to this device. So an object which is 15 centimeters in front of this lens, which is here. An object normally is placed to the left to the device. It doesn't have to be that way. We can place it anywhere correspondingly, but if we just follow the same agreement again and again, it makes thinking automatic. So here an object could have been also on the same side, on the left. And you can see the difference for the conversion device, for the conversion mirror, the focal point, the actual focal point, is on the same side with the object. For For that, I give a general answer. This is what you need to memorize for all situations. Positive, negative, positive, negative, positive, negative. See, for example, it says F is negative for a convex mirror. So yes. Now, where is the image? Well, we know what to do. We can draw a second ray, which should be bounced at the same angle. Draw an extension. This will be an image, an object, an image. And of course, for a convex mirror, it's a diverging device. An image cannot be real, never, ever. For every diverging device, images are only virtual. That's it. Now, what can we do? Just write an equation. 1 over F equals 1 over dO plus 1 over di. And use this equation, 1 over 30 plus 1 over 15 plus 1 over di. Now I'm just not walking, I'm walking specifically toward you. What did I do wrong? Yes, that's wrong. How do we correct it? See, life is easy when you know what to do. And now we just have to solve. That's mathematics. We've done this mathematics many, many times. I'm not going to finish it, but I just want to show that this number will be negative, because if we subtract 1 over 15, 1 over 15, two negatives, of course it has to be negative, because it's a virtual image according to the rules. For the virtual image distance di must be negative. If that is not the case, something is not right, we have to fix it. Well, so the image is virtual. Oops. Height, this is a space for the height. So we have a second equation. The first part is just a straightforward definition of a magnification. Second part has been derived geometrically from triangles, these triangles. You know what? Yeah, if I want to calculate this number, I have to finish this. So what do I have? 1 over di equals 15 negative 3 over 30, right? Negative 2, negative 3, 30. So the image distance will be negative 10. And I've been using centimeters for everything. So my answer automatically is in centimeters. It is negative, as it's supposed to, which is good, because the magnification has to be positive, because the image is upright. So HI, the height, has to be positive, and that is what we are looking for. Should be equal to this minus di over dO times HO. This minus the distance we just have found is negative 10. The object distance is 15, and the height is also 15. Right? 15 centimeters tall, negative 10, that was the answer. And the initial distance is also 15. So negative and negative makes it positive. Now, if you look at this picture, this is, yes. This one? This one? See triangles? Use them. And keep in mind that triangles relate sides. Each side has a positive length. So from triangles, the equation you can write is this. H, O, D, O, those variables are always positive because they related to an object, a real thing. But H, I, and D, I might be positive, might be negative, depending on the actual situation. And now you have to go back to this slide again, which tells us when the variables have to be positive, when the variables have to be negative, and in order to get rid of absolute value symbol, you must use that minus to relate them correctly. Yes? What did you say? I wrote, first of all, what happened to my slide? Two slides seem put together. Oh, all my handwriting moved to a different slide. So, okay, I will move it back after, but when we write this equation, we have to plug in two numbers, focal distance, and focal distance is -30, and the object distance, and the object distance is 15, that goes here. And then I'm subtracting -1/30 minus 1/15 is equal to 1/di. That's mathematics. And then I'm adding these together because I just multiply by 2 and by 2 to get a common factor. And -1 and -2 gives -3. The rest is, you have to think it through at a slower pace during office hours or at home. So, the important point is this picture shows that the size is about like 15. If you use squares, 1, 2, 3, no, 15, and this is a half of that, like 7.5. Yeah. Should be 10. Why? Precisely because this picture demonstrates the shape of this, the actual shape of this mirror. The model shouldn't show any curvature. In the model, the mirror should be straight, and the bending should begin here if you want to draw it exactly. And you only need to indicate the type of a mirror by bending the ends a little bit. So sometimes trying to be perfect actually is not very good. Yeah. Because you look at your picture and it makes an impression of a different size. But, okay, if you would use a ruler as accurate as possible, so this is 15, this is 30, should be twice of 15, and you draw all rays, oh, this is an extension, and second Again, you have to use a protractor, do it very accurately. I already didn't do it very accurately. Anyway, it should go like this. That's an actual ray. So, which means one simple thing. Use your diagram, but don't trust it completely. You have to check your diagram with your calculations. All right, so optical devices, it's a combination of several individual devices. This is a reflector invented by Newton. And you know that mirrors heavily used by magicians in theme parks. Here we have two mirrors. Both are concave mirrors. So this is an optical device. Light bounces off one mirror, then out of another mirror, then travels through in our eye. What we see is, well, that's what we call an optical illusion. So when I look straight down, I can see that little piggy, very expensive. But if I look aside, it looks like it's right here. I want to take it, and I can't. So just pass it around, please. But please be careful. They don't like being disturbed. And we are done with mirrors. So we know what refraction is, and we know how it's done. And let's take a look at some model of refraction. Again, you can see the links on on the blackboard. So with this applet, you can choose different media and see how would that affect the index of refraction. This is a model which tells us why the refraction is happening. Here you see like a marching band, and those dots represent light traveling down, but you can see that it travels at different speed. How does it affect the traveling through the boundary? Well, when they enter the region with a lower speed, they bend the total velocity, the direction. And this is basically how refraction works. Light travels with different speed in different media. And we saw yesterday that first, if we have a boundary between the medium number 1 and the medium number 2, first of all, what is the medium number 1? That's the medium in which light is approaching the boundary. So ray approaching the boundary. Next step, we have to draw the line which is perpendicular to the boundary. We call it normal, but we have to extend it into the second medium. Two media. Oh. See, I can read minds. And now you can read mine. So, we saw that, for example, light can bend toward the normal. To describe this phenomenon mathematically, what should we do? We should repeat this experiment many, many times with different angles. Small angle, large angle. Then what do we have to do? Well, we call it the angle of incidence, the angle of refraction. And we have to place numbers into a chart. And then we have to play with mathematically. And we did it, didn't work, didn't work, didn't work. So only successful attempt actually worked, which is calculating the sine of these angles and dividing them by each other. Yes?
Is the angle to the y-axis or the x, or does it not matter as long as
That's not the axis, that's a normal. That's how we measure this angle. It has to be measured from a normal to the ray. So it turns out no matter what angles we use, for this particular pair of media, this ratio remains the same, remains constant. That's just an experimental fact. So this is a law of refraction for two media. And of course, now we just have to figure out how to describe all possible media, air, water, glass, anything transparent. So what do? We do this. Well, technically, we use vacuum, but it also practically works in air. And then we use the medium we want to study, medium like water or glass or plastic. And for each medium we study, we calculate this ratio because it's constant. It is related to this medium. And we call it index of what? Refraction. It describes the refraction. That's it. And now, well, all we have to do, list all the media, water, glass, diamond. I wish I had diamonds. So, and for each we have a specific number, index of refraction for water. Well, very often just about 1.3. Does it have a unit? Please tell me. It comes from calculating two sines. Does it have a unit? No. That's a rare situation when a variable has no unit, just a number. Glass, about 1.5, diamond, 2.4, something like that. So these numbers just come from protractor and a laser pointer, that's it. But now what we can do, well, that we can play with the applet. We can summarize our statements. So we can make a conclusion in form of a statement. First of all, the statement says that when refraction happens, the normal and both rays should belong to the same plane. But also, for any two media, if we're calculating the product, the index of refraction of this medium times the sine of the angle in that medium, this product is the same. It's some kind of a conservation. Well, basically, as we know now, light always tries to travel by the shortest or the fastest path, so which leads to this. And these numbers, of course, have been measured and calculated. And this is the number related to the speed of light traveling in that particular medium. In a vacuum or in any very dilute gas, air, or any other gas, the speed of light is a fixed constant, about 3 times 10 to the 8 meters per second. But when it travels through a glass of water, it starts interacting with the particles, with atoms and molecules. That slows it down. The interaction between light and matter slows the light down. It travels slower, and this ratio is always greater than 1. And that's what the index of refraction is. So that's the law. And these are samples of some indices. vacuum or air and water. And this equation is so amazing. Thank you. Because basically with the laser pointer and the protractor, we can measure how fast light is traveling in water or in glass. We just have to measure index of refraction first using this law. It also has the name Snell's law, Descartes' law. We call it just law of refraction. So when we get this number, speed of light in vacuum divided by this number tells us the speed of light in that particular medium. The higher index is, the slower light travels because it interacts stronger. So the diamond slows it down significantly. Well, so let's just do a couple of examples. Light travels from air in water. This is the angle of incidence, which is 46. We are looking for the angle of refraction. So the law, the Snell's law, says this. It always says the same thing. It's a law. Now, for air, the index is 1. The angle of incidence is 46. For water, well, I just use 1.3. And we have to solve it for this angle. So we need to know how to calculate the inverse sine. Yeah. So basically, 1 times the sine of 46 degrees, not radians, divided by 1.3, and inverse sine of that should give us the angle. So please calculate it. You need to know how to use your calculator for this type of a calculation. Make sure your calculator uses degrees. Survey says, whoever has a number first, just tell it. Yep, about 34. That's it. Next example, what do we do? In the next example, we use the same two media. We just reverse the direction of light. So now we place the laser pointer into water. But does it affect the law? No, not at all. The law always says the same. This product for two media has to be the same. But what is different now? Now, the medium number 1 is water. Again, remember, the medium number 1 is the one in which light is approaching the boundary. So now this has to be 1.33. This has to be 46 degrees. This is 1 for the air. And now this is what we are looking for. That's the most important part. Figure out which medium is number 1. Maybe you should move closer. It looks like you have troubles to see what I'm writing. Yeah. So move closer. Okay. Yeah, I can make my life better, but I won't. So, the inverse sine of this product, 1.33 times sine 46 degrees. So please tell me the answer. Whoever first calculates the number. Let me check. 74. And now a question. So, we keep the same two media. The medium number 1 is water. The medium number 2 is air. But we changed the angle of incidence from 46 degrees to 76 degrees. So you have to take a calculator, replace a number 46 with a number 76. If you have a fancy calculator, you can erase 4, replace with a 7, and see what's going to happen. So I have to start my own calculation. But for you, I'm going to transfer, so less equals more. Less than 76 equals 76, greater than 76. Nothing. Yes. So, again, the law doesn't depend on the nature of the media. Again, the first medium is water. The angle of incidence is 76. Second medium is air. Angle of refraction is what we're looking for. So theta 2 is equal to the inverse sine of this product. So you have to take a calculator, type in I don't know why do I do it. I know the answer. So what does your calculator say? What does your calculator say? Yeah. You don't have a calculator. So you have to use a calculator to look at it. What's your calculator? Shows.
I pressed the clear button.
So you don't remember what did you see? What does your calculator say? What does your calculator say? What does your calculator say? Okay, it was a question, so let's see the distribution. It's basically about, do you know how to use your calculator? We do have a distribution. Okay. That's important. Negative 1.33. times sine 76 degrees. Second parenthesis has to be closed. Enter. What do we see? No, not error. Error 2. There's error 1 when you try to divide by 0. Error 2 is when you try to calculate the sine, or in this situation, how do I switch back? This product, again, now you can calculate 1.33 times sine of 76 equals, this is 1.29. What do we know about sine or cosine? It's limited between 1 and -1. It is never can reach 1.29. So if you're trying to calculate the inversed sine of a number, there's no answer. Does not exist. This number doesn't exist. That's why calculator get confused and says error. Yes?
So in this situation, the ray is
That's exactly what it means. It means that in this situation there is no refraction, because if refraction would be happening, law of refraction would give an angle. If an angle doesn't exist, that means the whole phenomenon doesn't exist. There is no refraction, but what is happening to light? It doesn't disappear. If it cannot get through, if it cannot get out, it means it gets back in the original medium. That's what we call reflection. In this particular case, we call it total reflection, because there is no light traveling out. It all travels back, reflected off the boundary. And this is the inner part of that medium, so we call it total internal reflection. Now, how do we calculate that angle which divides refraction into two different parts? So what is happening? If we have, and now actually I don't have to use water and air, I can use anything, and actually this is what I want to use. Medium number 1, medium number 2, and the index of refraction for the medium number 1 should be greater than the index of refraction of the medium number 2. What does it mean? It means if I write this equation, and if I solve it for the angle of refraction, this ratio is greater than 1, which means this angle should be greater than initial, than angle of incidence. So when a ray travels through the boundary from the medium with a higher index of refraction into the medium with a lower index of refraction, what is happening? Well, first of all, it can't travel just straight ahead like it was. It has to bend. How? Well, not like this, not like this. This type of bending would indicate, we call it air-water situation. Like we saw in this situation, ray bends toward the normal. But this is water-air, yes, situation. The ray should bend away from the normal. That's how it bends. So this is theta 1, angle of incidence. This is theta 2, angle of refraction. Has to be greater. But this angle has a limit. If we make the angle of incidence larger and larger, that would make the angle of refraction larger and larger. And at a certain point, it just has to reach that limit, 90 degrees. It cannot be greater than 90. That would be not refraction anymore. That would have been reflection. So this is how we can calculate that critical angle. This is when total internal reflection starts happening. This is the critical angle. Critical. So for theta critical, the equation is n1 times the sine of critical angle should be equal to n2 times the sine of 90 degrees at the maximum value for the angle of refraction. So the sine of this angle should be equal to just this ratio, which is actually less than 1, which is good. Yeah. And 1 over n2 is greater than 1. But this ratio is the opposite, less than 1. So this angle does exist. For example, yeah, here we can see an experiment with water-air. So when the angle of incidence is less than the critical, of course, refraction is happening. At the critical angle, now we see no light in the second medium, and if we go beyond the critical angle, this boundary begins acting like a mirror. Light just gets reflected. And again, that is being used for many different purposes. Well, let's solve this problem. So what we have is a light source in water, and well, that's surface of water. So what is happening to light? Well, rays which approach the boundary behave differently. This one just gets through, no bending, no refraction. But this one gets refracted, bends away from the normal. This one bends even more away. And at the critical angle, light doesn't get out anymore. That's it. So for the person looking down, only those rays which travel through the boundary can reach the eyes. So for that person, this would have been like a bright circle. And what we know? We know this. It's 1 meter. And we know the indices. For air, it's 1. And I know it's a second medium. For water, it's 1.33. Okay. And we need to calculate this radius. We said that, and we see a triangle. This is a triangle. And in this triangle, R over H should be equal to the tangent of this angle. That's not physics. That's geometry. But what physics says? Here, when that last ray approaches the boundary, it approaches the boundary at the critical angle to the normal. That's physics. But now we can look at these two angles, and again, that's geometry. those angles are equal. And now, if we want to calculate the radius, all we have to do is this. But how do we calculate the critical angle? Well, the sine of the critical angle should be equal to n2 over n1 or 1 over 1.33. Critical. Well, we can calculate it once. This is a critical angle for regular water. So that should be the inverse sine of 1 over 1.33. And that is inverse sine 1 over 1.33 equals about 48.8 degrees, or 0.75 degrees. That's it. So in this problem, we've used much more geometry than physics. So that's the answer. Now, what is not air around the prism? Yeah. What we have two different media, what might happen? Well, technically anything, right? So light travels in a yellow medium, then it gets into the prism made of some transparent material, glass, water, diamond. Yeah, I wish I had it. I would open my own school. And it leaves the prism, or maybe not, because as we know, here now, well, light always gets through when it approaches boundary at 90 degrees because there is no bending. Nothing can happen here. It always gets through unchanged, undeflected. But here, anything can happen. It might be completely reflected or might travel through and be bent. So this is our purpose, to figure out what might happen. Well, of course, we just need to draw the picture. So this is what we call N1, this is what we call N2. And the ray travels like this. There is no bending on this boundary, it just travels straight ahead. And bending starts on the second boundary here, if it starts. So what do we do? Well, we have to draw the normal. It is always the next step. We have a ray, now we have to draw a normal. Now, of course, we have to make an assumption, and let's say N1 is greater than N2. So it's like a water-air situation. Water-air case. And for this situation, ray should bend away from the normal. So light doesn't travel like this anymore. It has to bend away from original direction and away from a normal. So this is how it should travel if conditions are fulfilled, if there is no total internal reflection. Now, okay, that's a right angle. This angle is given to us, theta. So this angle will be 90 minus theta, and this angle will be 90 minus theta, which makes it what? Theta. So if we start writing the law of refraction, This is theta 2. This is theta 1, which is equal to the prism angle. This is what we call the base of the prism. So n1 times sine of theta 1 should be equal to n2 times sine of theta 2. Or n1 times the sine of the prism angle should be equal to n2 times sine of theta 2. Or sine of theta 2 should be equal to n1 over n2 times sine theta. What can we say about this ratio n1 over n2 times sine theta? It is a number, as any number. It have many different values, and the most important is 1. So it could be greater or equal than 1 or less than 1. And of course it is always positive. And how does it affect the phenomenon? If this ratio times sine is greater than 1, theta 2 does not exist. We know that, because the sine of any angle cannot be greater than 1. What does it mean? It means light doesn't get through. It means light will be reflected back at the same angle from the normal. And that includes n equals 1. Well, this whole thing equals 1. So only when this ratio is less than 1, theta 2 exists. In that case, light does travel through, bends in a certain way, and by the way, this angle from the original direction and the light, sometimes people use a Greek letter psi, this angle has a name, a deviation angle. By this angle, light was deviated from the original direction. Deviation. So, if we need to calculate a deviation angle for any device in any situation, so how do we call this in physics? You know it. You know it. It's a black box. Inside this black box can be anything. Lens, mirror, combination of those, anything. What we know is light travels through and deviates from the original direction. In that case, the angle between the original direction and the actual, that's what a deviation angle is. Well, so if we look at the prism, how does it act? Light bends and bends again. So for a standard situation, a glass, 1.5, air, when light travels through a prism like that, and we saw it in experiment, it bends, deviates from original direction toward the base of the prism. And by the way, we can flip this picture, and in that case, the deviation changes to the opposite. And that's how we make lenses. No. This is how we make lenses, because every lens basically is a combination of two or more prisms, like this. Light travels through, bends, travels through, bends. These rays cross. If we switch those two prisms, light travels through bends again, and these rays diverge, and this is a basis for a diversion and conversion lenses. So when we make a lens, basically we make a set of many prisms in a special shape. And as we saw, all rays traveling through conversion lens cross at the same point. We call it focal point. Distance from a focal point to the lens has a name, focal distance. If we have a diversion lens, rays diverge, and every time when the rays diverge, we use extensions to see where extensions cross. This point has a name, a virtual focal point, and the distance is negative. And now, basically, we can start talking about image formation by lenses. So this is just another new definition, which we're not going to use, but many students, pre-med students, should know it. Yeah. If you go to a store, buy glasses, or you go to an optician, so they don't use focal distances. Instead, they use optical power, and optical power is 1 divided by the focal distance of the lens. And optical power can be positive or negative. For conversion lens, focal distance is positive. Optical power is positive. For diversion lens, it's negative. And how do we use it? Well, glasses, contact lenses. So that's a survey, different types of the lenses. When we have a standard lens with edges thinner than the middle point, in air, it converges light. When the lens is thinner in the middle, in air, it diverges light. And we need 2 rays only to figure out everything about an image. So the ray number 1 always travels through the lens parallel to the principal axis because it has to go through the focal point. And the ray number 2, when it travels through the middle point of the lens, doesn't bend at all. That's it. For a divergent lens, we know the rule. Now it's a virtual focal point, and first we have to draw an extension, and then we can draw an actual ray. But because it's a transparent medium, if ray travels through the middle point, it just travels through without any bending. That's why the middle point is so special. That is why we always use it. So I always use just these 2 rays. And well, let's see how does it help us to draw a ray diagram. So we start from a principal axis, indicate the location of the lens, show the lens, show the type of the lens. Well, if it's a conversion lens in air, it should look like this. We don't do the whole shape, we don't draw it. We just indicate those parts, the ends. We assume that the surface looks like this, but we don't have to show it. But we do have to show the focal point. And again, we can place an object between the focal point and the lens, between the focal point and doubled focal point, or behind it. For all 3 situations, this ray, which travels parallel to the lens, parallel to the principal axis of the lens, has to go through the focal point. That's what the lens does. It is job. But other rays, and I'm going to do all cases in one. Other rays look differently. For example, this one. you can see these two rays do not converge. So we have to use extensions to see where extensions would cross. So this point tells us where the virtual image would be formed. Now, this ray, now we can see the crossing. So the image would be located, the actual real image would be located on another side of the lens, or yeah, I need a ruler, but basically something like this. For the same optical device, for the same lens, we have three different situations. What can we say about this image? Image is virtual, upright, and larger than the object. This one, well, it's hard to say from this picture because it's not drawn to scale, but it's definitely real, inverted, and technically should be larger, but okay. And this one is definitely real, inverted, and definitely smaller. And now we also see triangles. And now we go to the answer to the question from the yesterday: how does the lens mathematically relate? Well, first of all, a distance from an object to the lens is called the object distance. A distance from an image to the lens is called an image distance. The focal distance, the image distance, and the object distance are related by this equation. The only difference now, it has a different name. We not call it the mirror equation anymore. Now we call it the lens equation, or technically thin lens equation. And again, if you want to calculate how much larger or smaller an image is relative to an object, we have to introduce a physical variable quantity we call magnification. And the same triangles, the same geometry tells us that for magnification, we would have to use exactly the same equation. And the only difference is for the mirror, the real image is formed on the same size with the object. For the lens, the real image is formed on the opposite side of a lens. So that's it. Well, case 2, case 3. Case 4. Case 4 is for a divergent lens. The principal axis, the location of the lens itself, and a divergent lens in air would have a shape like this. But again, we do not draw the whole lens, we only show the ending. So this is a standard symbol for a divergent lens. Now which focal point we need? This one. On the same side with the object. Now, when the ray travels to the lens parallel to the principal axis, how does it bend? Away from the normal. But this is wrong. Why? Because the extension of this ray missing the focal point. Wrong. The extension should go through the focal point. So how do we fix it? We actually first draw an extension through 2 points, and then we continue with the actual ray. Second ray, we always use, travels through the middle point. nothing happening to it. And what we see now is a location of an image formed by an actual ray. But the second part is an extension, a fictional, imaginary line. So this image, an object, an image. This image is virtual. It's not formed by actual rays. It's a combination with a fiction. But it is upright and clearly is smaller. That's it. These are only diagrams we can draw for lenses. So the summary for a conversion lens, the summary for all lenses. These are only options existing for all possible mirrors and all possible lenses. So one way is just memorize them. Second way, of course, is being able to draw a diagram and looking at the diagram, extract all the important information. Question. Please tell me what you think. The answer, of course, is in the diagram. So you have to follow exactly the same strategy, which we used many, many times already today and yesterday. Starting from principal axis, so you have to take a pen or pencil, draw a horizontal line. Pick a point for a lens, draw the lens, show the type of the lens, show the focal point, place an object, and look at it. So, how should I show the ends of this lens? Down or up? Down or up? Into. Toward the middle. Now, focal length. Well, focal length is just a given number, 30 centimeters away from it. Placed 15 centimeters in front of. Okay, so it is placed here, and it's supposed to be 15, but 15 is less than 30. How do we know? We went to 4th grade school, I don't know, 5th grade, depending on the country. So, one ray travels like this through the focal point, second ray travels like this. This is a case when an object is placed between a focal distance and the lens. These rays do not converge. So they cannot form a real image. What's left? Virtual. And where is it? Well, we have to use extensions. That's going to be the image. This will be the image distance, which has to be negative, because for all virtual images, it has to be negative. But the height will be positive because it's upright. Now what can we write? 1 over 30 centimeters should be equal to 1 over 15 plus 1 over di. 1 over di is equal to 1 over 30 minus 1 over 15, which is times 2, 1 minus 2, negative 1 over 30. So this is negative 30 centimeters. Actually, my picture is not very accurate. My calculation tells me this image should be exactly at 30 centimeters away. So Well, I can fix it. But I can do it only now. Before I didn't know that. Well, and how tall is the image? Again, HI over HO is equal to this. So HI equals negative 15 over 15 times negative 30, which is 30 centimeters. Sometimes we may need to use this equation backwards. Sometimes we actually know HI, we know HO, and let's say DI, but this equation would give us how to calculate DO. So this equation relates 4 variables. As long as we know 3 of them, we can always calculate the 4th. Oh, I was right. I'm going to draw a diagram, and then probably that's going to be it. So, principal axis, the location of the lens. The lens, what kind of a lens? Diverging. Well, that's all my time. So thank you very much. So don't forget the lab. I'm going to start from this tomorrow. Thank you for keeping this for me. If you have any questions about an exam, I'm going to finish this. I'm going to go to my office hour, and we can talk there.